Working? Okay. Our first speaker this afternoon is Domani Sharkey, who's joined us from Caltech this summer. Domani's been working with Josh, and she'll tell us today about their project together, The Hunt for Binary Stars in the Darkest Galaxies.
Thank you for the introduction, Gwen. So to understand why we're looking for binary stars in the darkest galaxies, we first need to talk a little bit about dark matter. Dark matter is the mysterious substance that comprises over 80% of all mass in the entire universe. If we look at this distribution of energy in the universe in the pie chart over there, the dark matter part of it comprises the large majority of all the matter that we see in our universe. And the normal matter that we're familiar with is only 5% of that entire fraction. And dark matter is incredibly important because it's responsible for the present structure of our entire universe. Without the gravitational influence that it has on all of that matter, we wouldn't have galaxies, stars, planets, or anything like that. So in that sense, you could say that it's the reason that we're even here. And yet we know next to nothing about it. It's one of the biggest scientific mysteries of our entire day. But luckily for us, there's something called ultra-faint dwarf galaxies that exist, which are amazing laboratories for studying dark matter because they're over 99% dark matter. So they're the most dark matter dominated systems known, which means we essentially have access to systems where dark matter is the primary element at play. So any behavior that we study in these galaxies can be attributed solely to dark matter, which makes them amazing for the investigation of this mystery. And one of the key steps involved in using ultrafaints to study dark matter is measuring the dark matter that's actually inside them. And since they're just 99% dark matter, that's basically the same thing as measuring just the dynamical mass of that galaxy, which we can do by first calculating their stellar velocities, using that to get to a velocity dispersion, and then using that to derive a dynamical mass for that galaxy, which again is just approximately the dark matter that's in that galaxy. But as we can see from these steps here, the velocity dispersion is incredibly important to this whole process, which means that if something is inaccurate along these steps, it will lead to inaccurate dark matter measurements, which presents a problem if there's a binary star, because we use those stellar velocities to get to our velocity dispersion in order to get to the dark matter mass. And binary stars present a danger because their orbital velocities can actually be much greater than the velocity dispersion that we obtain for our galaxies, which means they can inflate that value and lead to inaccurate dark matter measurements. If we look at this plot over here of an example of a binary star in the dwarf Hercules, where we're plotting the radial velocity of that binary star over time, you can see that the orbital velocity gets up to about 15 kilometers per second, whereas the velocity dispersion of that galaxy is more on the order of about 5 kilometers per second. So it can have that effect on our calculations where it's greatly inflating them, and then that will lead to inaccurate dark matter measurements. So one thing that we can do to kind of account for this problem is try and put a very valuable constraint on the fraction of binary stars that are actually found in ultrafaints, because we can use that constraint to kind of tell us more about how many binary stars we're expected to find in these galaxies, and just what the distribution of those is like. So that's what we did for this project. We just tried to take a sample of a bunch of stars from ultrafaints. Specifically, we took 28 of the brightest stars from 12 local ultrafaint dwarf galaxies, and then we essentially just tried to find the binary stars within that sample. We took the observations over approximately a 5-year time baseline so that we could have an accurate amount of time to kind of test for this velocity variability. And we took our data from the high resolution Mike spectrograph. We got spectra for each observation that we took, which looks like this little plot over here, where it's essentially the intensity of the light or the flux of the light coming in with dips in that called absorption lines that show us what wavelengths that light is being absorbed at in the gas of that star. And because it's a high resolution spectra that we obtained, that meant we were able to get a sufficient amount of velocity precision that we were able to get multiple velocities for a single observation of a star because the light that was coming in was split up into multiple different diffraction orders. So again, we had our sample of stars, and our goal was to find the binary stars within that sample by finding the stars with varying velocities. So to actually measure the velocities of a star, what we can do is employ something called the Doppler effect. And if you're not familiar with the Doppler effect, it's essentially just a relationship between the wavelength shift that we see between absorption lines of a source of light and that source's velocity. So for example, here's a spectrum that we had for one of the stars in the Carina 2 dwarf galaxy, and we were able to kind of compare it to a rest spectrum that's called a template spectrum. And that can give us a comparison value to get a wavelength shift in the absorption lines that you see over there. And we can use that wavelength shift to tell us what the velocity of that star must be. So when we do this for all the stars in our sample, we get velocities for all the observations of those stars in our sample. And to be more specific, here's an example of a figure that we generated again for another Carina 2 star, where every single data point on this plot here is a radial velocity that we got for it. And the reason that there's multiple of them is, again, because the light was split up into multiple diffraction orders, and we were able to get velocities for each order. The blue triangles indicate the bluer orders with just bluer wavelengths, and the pink stars indicate the redder orders with the redder wavelengths, and the black circles indicate which orders we actually included in our analysis. Some of them were excluded for various reasons, including not having a high enough signal to noise ratio, and also for the orders that had too many telluric absorption features, which is just the Earth's atmosphere impacting them, that could mess up our analysis. And then we were able to, from this, get multiple velocity related values for that star, including the heliocentric velocity and the standard deviation and some other ones. And we used a software developed by G et al. 2020 that we modified and improved the precision of in order to get this data. So once we did that for all the stars, what we essentially had was, for every single star in our sample, a set of velocities over a time period. And again, we're trying to find the binary stars in this entire sample. So what you can do is look at this set of velocities for like a single star and see whether the velocity is staying consistent over time. And the way we did this gave us a statistical analysis of the likelihood of the binarity of that star. And specifically, we used a chi-squared goodness of fit analysis, where the fit that we were kind of testing was just that the velocity of that star was constant. So computing that analysis, we got a value that tells us how likely it is that the star's velocity is constant. And if the likelihood of that was low enough, we said that it rejected our hypothesis that the star's velocity was constant, because it just means that the probability of the star's velocity being constant is so low that it indicates evidence of a binary star. It means the velocity is varying significantly. And that significant velocity variation is the evidence of binarity that we were looking for. And to further emphasize this, we have, oh no, go back. To further emphasize this, we have a plot of two stars that we had in the Carina 2 dwarf galaxy, where one of them showed evidence of being a binary and the other one did not. And the green is the one that did not show evidence of being a binary. And you can see that its velocity kind of just stays constant over the same time period, versus the one that showed evidence of binarity, where it kind of just goes all over the place. And once we got those probability values for every single star in our sample, we found that 29% of them showed evidence of binarity. And specifically, we plotted the distribution of those probability values, where again, the probability is just how likely is it that this star's velocity is constant. And you can see the peak over here to the left that shows the stars that had a low enough probability that it was more likely that they were binary stars. And specifically, the pink vertical line there is the threshold that we used for binarity, where essentially that's just saying that if it had less than a 0.01 probability of having a constant velocity, then we said it showed evidence of being a binary star. And what this means for our project is that every single ultrafaint that had a star that showed evidence of binarity will need to have its dark matter mass completely reevaluated, because as we saw, the presence of a binary star can significantly inflate the velocity dispersion obtained for that galaxy and then make our dark matter mass inaccurate. So we'll have to reevaluate those dark matter masses that were previously obtained. And on that note, it shows us how critical it is to using ultrafaint dwarf galaxies for dark matter investigations, that we account for the possibility of having binary stars in our ultrafaint dwarf galaxies. And specifically, we want to have spectroscopy taken of these galaxies over a sufficiently long amount of time so that we can accurately assess whether the stars that we're observing are going to be having velocities that are varying, because it will have a significant effect on the values that we obtain for those observations. And finally, that 29% that we got, again, puts a very valuable constraint on the fraction of kinematically relevant binary stars in ultrafaint dwarf galaxies, which just means that they had short enough orbital periods where their orbital velocities are high enough to actually have an effect, a significant effect on the velocity dispersion. For example, if a star has a super long period, then it can essentially just be treated the same as a single star in terms of using it for calculating a velocity dispersion. And in the future, this constraint that we got can be used to more precisely measure the dark matter in ultrafaint dwarf galaxies in general. And this is especially important because we know so little about dark matter. It makes it even more important to have that type of precision in our measurements and in our investigations of dark matter, because we just have such little knowledge about it. So we can use this constraint that we got to make our investigations in the future of dark matter that much more accurate. Thank you.
Domani.
Thanks, Domani. This was really, really nice. I wanted to ask about the plot you showed of the velocity in the different orders. In
That one?
Yes. So why are the velocities so different in the different orders? It's the same star that we're observing.
Yeah.
So why are they different, and how do you take into account all of that to obtain a final radial velocity at a given epoch for a star?
Yeah, thank you for that question. So you can kind of see a trend in the velocity with wavelength here, especially for the redder orders. And that's actually the effect of like atmospheric dispersion. As the light's coming in, it can disperse the light. So that's the trend. That explains the trend that you see there. But essentially what we did is the uncertainties that we took for our velocity values already kind of account for that effect, because we took a sort of weighted standard deviation of all the velocities that we had. So it includes the effect of that atmospheric dispersion in our analysis. And of course, it's something in the future we could go back and increase the precision of our results by correcting for that. But our current analysis already incorporates that effect into the uncertainties that we used.
Thank you, Domani. That fraction of 29%, was that just constant over all ultrafaints? Do you see a higher percentage in other ultrafaint dwarf galaxies or a lower percentage in others? And does it just average to 29, or is it like 29 in each of them?
Oh, I think I understand what you're saying. So that was just the total like fraction of, like, we were treating all ultrafaint dwarf galaxies as just like not specifying them like by actual galaxy, but just a total sample of galaxies. And then so we had like 28 stars, and then it was 8 out of 28 of them showed evidence of binarity, which is where the 29% came from.
Okay.
Does that make sense?
Yes.
Okay.
Yeah, thank you.
Thanks. That was a really excellent talk. It's a kind of related question to Erica's. Is this kind of consistent with what you'd expect from stellar population modeling of these galaxies, or is that something that you compared to, or maybe?
I mean, sort of. There have been studies that say it's more likely that, you know, these super old galaxies that are metal poor are more likely to have binary stars. So that kind of can contribute to maybe we're expecting to have a larger fraction of binary stars in general. But it is kind of a high fraction, which is not exactly what we were expecting. So yeah.
Let's thank Domani again.